Hello friends, and welcome to the video number 5 of the video series Vibration of Multi-Degree of Freedom Systems. In this video, we are going to discuss about the modal analysis of the multi-degree of freedom systems kind of vibration. So let us start with the topic. So before starting this topic, we'll consider the following type of 2-degree of freedom system, which is free and undamped. Now this is the system. This is your system in which we have 3 springs connected in parallel along with 2 masses. So we know because this kind of arrangement consists of 2 different masses, so the degree of freedom will be 2 for this system, and we have 3 springs connected in parallel. The mass 1 will have a vibrational displacement of x1 with the acceleration x1 double dot. Similarly, the mass 2 will have the vibrational displacement x2 along with the acceleration x2 double dot. Now, for the instant in which the mass m1 is moving in downward direction and mass 2 also moves in downward direction, we'll draw the free body diagram of the system. So in free body diagram, we need to show the forces which will act over the masses m1 and m2. So here we have taken the mass m1 first. Now the mass m1 is having a downward displacement x1 double dot at the particular instant. Okay, when this mass m1 is moving in downward direction with the displacement x1, there will be a restoring force generated in the spring K1, right? Now the magnitude of this restoring forces will be K1 x1, and because the mass m1 is moving in downward direction, the restoring force generated in spring K1 will be in upward direction. The force generated in the spring K1 will be in upward direction. Alright? Okay. Now when the mass m1 will move in downward direction, the spring K2 will also feel a restoring force. The magnitude of this restoring force will be K2 into net displacement of this spring, net deformation of the spring K2. The amount of force generated in the spring K2 will be K2 into net displacement of the spring, net deformation of the spring. Now, how much is the net deformation of the spring K2? See, the displacement of mass m1 is in downward direction, the displacement of mass m2 is in downward direction. So the net deformation of the spring K2 is x1 minus x2, right? The net deformation of this spring will be x1 minus x2 or x2 minus x1. Both are right. X1 minus x2 is also right. X2 minus x1 is also right as the net deformation of the spring K2, but their directions will be opposite. The direction of x1 minus x2 will be opposite to x2 minus x1. Right. Okay. Now, because right now we are considering the mass m1, we know the restoring force generated in the spring K2 will be also in upward direction because the mass m1 is moving in downward direction. So I'll draw the restoring force generated in the spring K2 is in upward direction. For mass M1 I'm talking. For mass M1. Right? Okay. Now, so whenever we are talking about mass M1, it is having a downward displacement x1. The restoring force generated in the spring K1 is K1 x1 in upward direction. The restoring force generated in spring K2 is K2 into x1 minus x2, that is also in upward direction. Okay. Now we'll come to mass M2. Mass M2 is also moving in downward direction for this instant. Now as mass M2 is moving in downward direction, the spring force in the spring K2 will be in upward direction because that is restoring force. Similarly, the restoring force in spring K3 will also be in upward direction. The force here will be in upward direction in spring K3. The force in spring K2 is also in upward direction. For mass M2 I am talking about right now. Okay. So now mass M2 is moving in downward direction with the downward acceleration x2 double dot. The restoring force generated in the spring K2 is in upward direction. Now the net deformation of the spring K2 for mass M2 we are going to take as x2 minus x1. I told you both x1 minus x2 and x2 minus x1 are same magnitude wise, but they will be opposite in direction, right? So for mass M2, the net deformation in the spring is x2 minus x1, and the restoring force generated in the spring K2 will be K2 into x2 minus x1 in upward direction. Similarly, the restoring force generated in the spring K3 will be K3 into x2 in upward direction once again. Alright, so we have covered all the forces on both the masses. So this is the free body diagram. This one is the complete free body diagram of the system. This one. This is the complete free body diagram of the system. Now with the help of free body diagram, we can easily get the equations of motions for this kind of system. And now to get the equations of motions, we can apply Newton's second law of motion or D'Alembert's principle to the given system. I prefer applying Newton's second law of motion. So from the free body diagram, we can write the vector sum of all the forces is equals to 0. This is the statement of the Newton's second law. The vector sum of all the forces in any particular direction is equals to mass into acceleration in the same direction. This is the Newton's second law of forces. Because I am taking vector sum, I need to show the vector sign over force and the acceleration, right? So we know the direction of the displacement is the positive direction to apply Newton's second law of motion. So here we know mass m1 is having displacement in downward direction, mass m2 is also having the displacement in x2 direction, x1 and x2 both are in downward direction. So downward direction is the positive direction to apply Newton's second law of motion. The downward direction is a positive direction to apply Newton's second law of motion. And upward direction is negative direction to apply Newton's second law of motion, right? Downward direction is the positive direction. Upward direction is the negative direction. to apply Newton's second law of motion. Downward direction is the positive direction, upward direction is the negative direction. So the forces which will act in downward direction has to be taken as positive forces. The forces which are acting in upward direction, they have to be taken as negative forces to apply Newton's second law of motion to the given system. Now, talking about mass 1, the force K1x1 is acting in upward direction. So I'll write minus K1x1. The force K2 into x1 minus x2 is acting in upward direction. So I'll write minus K2 into x1 minus x2. And it is equals to m1 x1 double dot. x1 double dot is the acceleration of mass m1. Now for the mass m2, the force K2 into x2 minus x1 is acting in upward direction. So I'll write minus K2 into x2 minus x1. Similarly, the force K3 into x2 is also acting in upward direction. So I'll write minus K3 into x2, and that should be equals to m2 into x2 double dot. Again, x2 double dot is the acceleration of mass m2. Now, so I'll rearrange the equations of motions. So here I'm just simplifying the equations of motions. Now this is the simplified version of the equations of motions, where I have taken all the variables to one side of the equation, and that is equals to 0. Now after rearranging the terms, I'll get the equations of motions in the form m1 x1 double dot plus k1 plus k2 into x1 minus k2 into x2 equals to 0. And the second equation is m2 into x2 double dot minus k2 into x1 plus k2 plus k3 into x2 equals to 0. Now these are the equations of motions. For my system, these are the equations of motion. So I'll name them by equation number 1. So this entire setup of the equations, this setup of the equations are the equations of motions for me. So these are the equations of motions. So whenever I'll talk about the equations of motions, I'll talk about the equation number 1 here. Now what I have done, I have rearranged these equations of motions in matrix form. So how I have arranged? See, I have taken a matrix, 2 by 2 matrix I have taken. It's a matrix of the form 2 by 2. 2 rows are there and 2 columns are there. So it's a 2 by 2 matrix. I have taken the matrix in the form m1 0 0 m2. Then I have multiplied this matrix with a column matrix of x1 double dot x2 double dot. It's a column matrix of 2 cross 1. So if we'll take the product, this is 2 cross 2, this is 2 cross 1, the product will be 2 cross 1 matrix. So again you are going to get the same thing, this one. This is m1 into x1 double dot plus 0, right? Here it will be 0, here it will be plus m2 into x2 double dot, and this has to be added with the product of these two matrices, right? So I have taken one matrix m1 0 0 m2 multiplied by a column matrix x1 double dot and x2 double dot, plus then I have taken the matrix as k1 plus k2 minus k2 minus k2 and k2 plus k3. These are the 4 elements of the matrix. Again it's a 2 cross 2 matrix multiplied by a column matrix of x1 and x2, the deformation part, and it is equals to a column matrix 0 0, right? So if you solve this entire matrix product and you will add them, you will equate them with the 0 column matrix, you will get the same equations of motions. You can solve them, you will get the same equations of motions. So I can conclude the same equations of motions I can write in the matrix form. This is the matrix form of the equations of motions. So equation number 2 is also the equations of motions. Equation number 1 is the equation of motion. Equation number 2 is also the equations of motion for the system, but in matrix form. These are the equations of motions in matrix form, right? Now here the matrix M100 M2 is called as a mass matrix, and the matrix K1 plus K2 minus K2 minus K2 K2 plus K3, it is called as the stiffness matrix. In the set of equations of motions, this 2 cross 2 matrix of M100 M2 is called as mass matrix. The 2 cross 2 matrix of K1 plus K2 minus K2 minus K2 K2 plus K3 is called as stiffness matrix. Okay, now once again we will talk about the equations of motions only. Okay, so now leave that. So we have done till the matrix form of the equations of motions. Now I'm going to assume the solution of equations of motions. Now what may be the solution of equations of motion? See here. Observe equation number 1. Here I have the variable as x1 and x2. In this equation also I have the variable as x1 and x2. So the values of the formula of x1 and x2 will be the solution of the equations of motions. Now what I'll do, I'll assume the solution of the equations of motions, means the form of x1 and x2 I'll assume. Now I have assumed x1 to be a1 cos omega n1 t, and I have assumed x2 to be a2 cos omega n2 t. We know the displacement, velocity and acceleration of vibrational motion is a function of time, is always a function of time, and vibration represents the simple harmonic motion. So I can assume the values for the time dependent displacement x to be a sin omega t, a cos omega t, a sin omega nt plus phi, a cos omega nt minus phi. These 4 forms I can assume easily. So I have taken one form out of them. I've assumed x1 to be equals to a1 cos omega n1 t. I've assumed x2 to be a2 cos omega n2 t, where a1 and a2 are the amplitudes of x1 and x2 vibrational displacements. Omega n1 and omega n2 are the natural frequencies of the vibrational displacement x1 and x2. Now once I have assumed x1 and x2, I can write x1 double dot and x2 double dot. X1 double dot will be the double differentiation of x1, that is a1 cos omega n1 t, and we are going to get this as minus omega n1 square a1 cos omega n1 t. Similarly, x2 double dot is minus omega n2 square a2 cos omega n2 t. Now once we got x1 double dot and x2 double dot, x1 and x2 will put all of them in equations of motion, that is equation number 1 only, without matrix form. So in equation number 1 I'll put x1 double dot, x2 double dot, x1 and x2, these values I'll put in equation number 1. Now I can write my equation number 1 to be minus m1 omega n1 square plus k1 plus k2 whole multiplied by a1 cos omega n1 t minus k2 a2 cos omega n2 t, and this is equals to 0. This one is equals to 0. Similarly, I can write the second equation as minus m2 omega n2 square plus k2 plus k3 whole multiplied by a2 cos omega n2 t minus k2 a1 cos omega n1 t equals to 0. Now these are the equations of motions, right? Now in both the equations, what I'm going to do, I'll assume omega n1 and omega n2 to be equal, and both are equal to omega, right? I can take this assumption is valid. If omega n1 and omega n2 are different, after solving these equations of motions, I'll get their different values. But for this instant, I can assume them to be same. If they are having the different values, after solving equations of motions, I'll get different natural frequencies, two different natural frequencies, two distinct natural frequencies I'll get. And then my assumption will be invalid. That's it. So for time being, I'll assume omega n1 is equals to omega n2. Both are equals to omega. Now putting omega here, so the equations of motions will be modified, and it will be minus m1 omega square plus k1 plus k2 whole multiplied by a1 cos omega t minus k2 a2 cos omega t equals to 0, minus m2 omega square plus k2 plus k3 whole multiplied by a2 cos omega t minus k2 a1 cos omega t equals to 0. Now here I'll take cos omega t common, so 0 by cos omega t will be 0. Here also I'll take cos omega t common, so 0 divided by cos omega t once again will be 0. Now my equations of motions have been modified to minus m1 omega square plus k1 plus k2 whole multiplied by a1 equals to k2 a2. This k2 a2 will be remaining here, so it is minus k2 a2 here. I'll take it this side to right hand side of the equation, it will become plus k2 a2. Similarly, it will be minus m2 omega square plus k2 plus k3 into a2 equals to k2 into a1, right? Now see these equations, you need to observe it here carefully. Now here, if I want to take the ratio of a2 by a1 from this equation, so this will be a2 by a1 will be equals to minus m1 omega square plus k1 plus k2 divided by k2. Now from this equation, if I am writing a2 by a1, so this will be equals to k2 by minus m2 omega square plus k2 plus k3, right? So what is this a2 by a1? a2 by a1 is the ratio of amplitudes, the ratio of corresponding amplitudes of x2 and x1, right? These are the ratios of corresponding amplitudes of two different vibrational displacement of two different masses in the same system, right? And we are getting two different values of a2 by a1. The one value of a2 by a1 is minus m1 omega square plus k1 plus k2 by k2, and another value of a2 by a1 is k2 by minus m2 omega square plus k2 plus k3. Now I'll name these two equations as equation number 3, right? I'll name these equation as equation number 3.